You watch the night sky expecting constancy. Stars hold their positions, planets follow predictable paths. Then, something breaks the rules. In early 2020, astronomers spotted Comet 3's Atlas racing toward the sun at impossible speed. For weeks, it brightened faster than any comet on record, and then it vanished. Not slowly, like comets usually do. It died in days. What killed the most promising comet in decades? Why did it brighten so fast in the first place? The answer rewrites what we thought we knew about these cosmic wanderers. If you value documented space science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory and the International Astronomical Union. Now back to the story. 3I/Atlas first appeared on December 28, 2019. The asteroid terrestrial impact last alert system spotted a fuzzy dot moving through Lynx constellation. Distance, 400 million kilometers from Earth. Brightness, magnitude 19.6. Invisible to human eyes, but the math told a different story. This object was falling toward the sun at 60 kilometers per second. Its orbital period stretched back 26 million years. This wasn't just any comet. This was a visitor from the outer reaches of our solar system. The Atlas survey operates from 2 telescopes in Hawaii. Each night, they scan 8,000 square degrees of sky, hunting for moving objects that could threaten Earth. On that December evening, the automated software flagged object A/2019 L3. Initial observations suggested an asteroid, then spectroscopic analysis revealed the telltale signature of water vapor and dust, not an asteroid, a comet. By February, Atlas had crossed inside Jupiter's orbit. It should have been getting brighter slowly, following the standard comet formula. Instead, it exploded with light. Magnitude dropped from 19 to 12 in 2 weeks. That's a brightness increase of 1,600 times. Professional observatories swung their dishes toward Atlas. Amateur astronomers started posting photos online. Something extraordinary was happening. The brightening violated astronomical expectations. Most comets follow a predictable curve as they approach the sun. Their brightness increases proportional to the inverse square of their distance, modified by sublimation rates of surface ice. Atlas ignored these rules. Between January 15th and February 1st, it brightened at a rate suggesting a nucleus diameter of 40 kilometers, but orbital mechanics indicated something much smaller, perhaps 4 kilometers across. The discrepancy puzzled comet specialists worldwide. Either Atlas was unusually rich in volatile materials, or something else was driving its spectacular light show. Ground-based telescopes in Chile, Spain, and Australia began tracking it continuously. The European Southern Observatory allocated precious observation time on their Very Large Telescope Array, NASA's Hubble Space. Telescope joined the campaign. The brightening continued through March. By the 15th, Atlas reached magnitude 8.5, visible to binoculars. Predictions put it at magnitude -5 by late May, brighter than Venus, visible in daylight. Space agencies prepared observation campaigns. This could be the comet of the decade. Amateur astronomers contributed crucial data during this period. Gerald Raman in Austria captured detailed images showing Atlas developing a classic comet tail. Michael Jaeger, also in Austria, documented rapid changes in the coma structure over just hours. These observations revealed something troubling. The coma wasn't behaving like a normal comet. It showed irregular brightness patterns and asymmetric gas jets. Professional analysis confirmed the amateurs' suspicions. Spectroscopy revealed unusual ratios of carbon monoxide to water vapor. Most comets show consistent molecular ratios as they approach the sun. Atlas displayed wild variations from night to night. The nucleus was either extremely heterogeneous in composition, or it was beginning to fall apart. Then Atlas started breaking apart. If you value space discoveries that challenge our understanding, subscribe and let us know which city you're watching from. This research comes from the European Southern Observatory and Hubble Space Telescope data. Back to the story. March 22nd, amateur astronomer Jose de Queiroz in Brazil noticed something wrong. Atlas looked elongated in his telescope images, not the clean circular coma of a healthy comet. By March 25th, the Hubble Space Telescope confirmed it. Atlas had split into at least 4 separate pieces. Each fragment glowed with its own tail of gas and dust. Hubble's sharp vision revealed the breakup in unprecedented detail. The main nucleus had separated into fragments designated A, B, C, and D. Fragment A measured roughly 800 meters across. Fragment B was smaller, perhaps 400 meters. Fragments C and D barely registered above background noise, chunks of ice and rock maybe 50 meters wide tumbling through space. The fragmentation accelerated. By April 6th, ground-based telescopes counted 30 distinct fragments scattered across 2 arc-minutes of sky. That's 60,000 kilometers of debris. The original nucleus had completely disintegrated. What started as a single 4-kilometer-wide chunk of ice and rock became a swarm of house-sized boulders tumbling through space. Each piece followed a slightly different trajectory. Solar radiation pressure and outgassing affected smaller fragments more than larger ones. Within days, the debris cloud stretched across hundreds of thousands of kilometers. Some pieces brightened as fresh ice surfaces got exposed to sunlight. Others faded rapidly as their volatile materials boiled away. But here's what puzzled astronomers most. Atlas didn't fade immediately after breaking up. Many fragments continued brightening for days. This violated every model of comet behavior. When comets fragment, they typically dim rapidly as their surface area decreases, and internal ice gets exposed to solar radiation. Atlas did the opposite. The Spitzer Space Telescope provided crucial infrared observations during the breakup. These revealed that fragment temperatures varied dramatically. Some pieces glowed at minus 40 degrees Celsius, while others registered minus 120 degrees. The variation suggested different compositions or internal structures among the fragments. Radio telescopes detected hydroxyl emissions from the fragments. This molecule forms when sunlight breaks apart water vapor molecules. The intensity of these emissions allowed astronomers to estimate gas production rates. At peak activity, Atlas fragments were producing 300 kilograms of water vapor per second. For comparison, Comet Halley, at its brightest, produces about 10 tons per second, 30 times more, but from a nucleus 10 times larger. The answer lies in the comet's internal structure. Atlas wasn't a solid chunk of ice. It was what astronomers call a rubble pile, thousands of smaller pieces held together by weak gravity and frozen gases. As it approached the sun, heat didn't just melt the surface. It penetrated deep into the nucleus, vaporizing internal ice deposits. This created pressure that pushed the fragments apart from within. Computer models of the breakup process revealed the likely sequence of events. As Atlas approached the sun, solar heating penetrated several meters into the nucleus. Internal ice began sublimating, creating gas pressure. The weak structure couldn't contain this pressure. Cracks formed, widened, and eventually split the nucleus apart. Each fragment became a miniature comet. Fresh ice surfaces suddenly exposed to sunlight vaporized rapidly, creating bright comas and tails. The total surface area increased dramatically. More ice meant more gas production. More gas meant more brightness. For a few weeks, fragmentation actually made Atlas brighter than it would have been as a single object. This burst of activity consumed the comet's reserves. Comets are finite reservoirs of ice and dust. Unlike stars, which burn fuel in controlled fusion reactions, comets simply evaporate their substance into space. Once the ice is gone, they become dark, inert rocks. Atlas burned through its volatile materials in a spectacular but brief display. By May 1st, most fragments had faded below telescopic visibility. A few larger pieces persisted into June before vanishing completely. What should have been the year's brightest comet became a cloud of invisible debris continuing its ancient orbit around the sun. The death of Atlas provided unprecedented data about comet internal structure. Most comets don't fragment so completely or so close to Earth. Previous breakup events occurred too far away for detailed study, or the fragments remained too close together to resolve individually. Atlas offered astronomers a unique laboratory for understanding how these ancient objects hold together, or fall apart. Analysis of the fragmentation pattern revealed that Atlas likely formed through gradual accretion rather than catastrophic collision. The pieces showed no signs of shock heating or compression that would indicate violent formation. Instead, they appeared to be loosely bound collections of smaller chunks that never fully consolidated into a solid mass. The story of Atlas reveals something profound about long-period comets. These objects spend millions of years in the outer solar system at temperatures near absolute zero. Their internal structure reflects that deep freeze, loosely bound materials that never fully consolidated. When they finally fall sunward, the sudden temperature change doesn't just melt their surfaces, it tears them apart from within. Orbital calculations traced Atlas back to its previous visit 26 million years ago. During that epoch, the sun was slightly dimmer and the solar system looked very different. Earth's continents occupied different positions. Life existed, but complex ecosystems were just beginning to evolve. The ice that formed Atlas witnessed the rise and fall of countless species. The comet's composition also tells a story about solar system formation. Spectroscopic analysis revealed isotope ratios consistent with formation in the outer regions of the protoplanetary disk. The deuterium to hydrogen ratio in Atlas water vapor matched that found in other Oort cloud objects, but differed from comets originating in the Kuiper belt. This supports models suggesting different formation zones for different comet populations. Atlas also confirms a disturbing trend. Many bright comets discovered in recent decades have disintegrated before reaching peak brightness. Comet Ison in 2013 broke apart just before perihelion. Comet Linear in 1999 fragmented into dozens of pieces. Comet West in 1976 lost significant mass to fragmentation, but survived long enough to put on a spectacular show. The pattern suggests that truly spectacular naked-eye comets may be rarer than we thought. The ones that survive intact to give great shows might be the exception, not the rule. Comet Hale-Bopp in 1997 remained intact because of its unusually large size, 60 kilometers across compared to Atlas's 4 kilometers. Bigger comets have stronger gravity to hold their components together. Modern telescopes detect comets years before they reach peak brightness. This creates expectation and disappointment when objects like Atlas fail to deliver. But it also provides unprecedented data about comet composition and behavior. Every fragmentation event teaches us something new about these ancient time capsules from the solar system's birth. The Atlas discovery also highlighted the importance of automated sky surveys. Human astronomers could never scan enough sky fast enough to catch faint comets billions of kilometers away. Computer algorithms process millions of images each night, comparing them to reference catalogs and flagging anything that moves or changes brightness. Ground-based observers worldwide contributed to Atlas science. Professional observatories provided high-resolution spectroscopy and precise astrometry. Amateur astronomers delivered continuous monitoring that revealed rapid changes invisible to scheduled professional observations. The combination created the most complete record of a comet breakup in astronomical history. The data from Atlas will influence comet science for decades. Theoretical models of comet structure now must account for extremely weak binding forces and heterogeneous compositions. Mission planners designing future comet encounters will use Atlas data to predict which targets might survive close approach and which might disintegrate. The death of Atlas wasn't a failure. It was a revelation. 26 million years ago, when this comet last visited the inner solar system, the first human ancestors were learning to use tools. The ice and rock that formed Atlas predates complex life on Earth. Its final moments gave astronomers a front-row seat to processes that have been shaping our solar system for 4.5 billion years. Future sky surveys will discover thousands more long-period comets like Atlas. The Legacy Survey of Space and Time, scheduled to begin operations in 2025, will detect comets 10 times fainter than current surveys. Many of these distant visitors will likely follow Atlas's path, brightening rapidly, raising hopes, then fragmenting before reaching their full potential. In 2047, Atlas fragments will reach their farthest point from the Sun before beginning another 26 million year journey home. By then, Earth may be unrecognizable. Human civilization might have spread to other worlds, or vanished entirely, but somewhere in the darkness beyond Neptune, pieces of this ancient wanderer will continue their eternal dance, carrying secrets from the solar system's violent birth. The Atlas breakup revealed something else crucial about comet science. Traditional brightness predictions assume comets are dirty snowballs with predictable sublimation rates. Atlas proved that many long-period comets are more like cosmic sandcastles, fragile structures held together by surface tension and weak van der Waals forces between dust grains. Laboratory experiments at NASA's Goddard Space Flight Center recreated conditions inside fragmenting comet nuclei. Researchers placed ice dust mixtures in vacuum chambers, then heated them to simulate solar warming. The results matched Atlas observations perfectly. Internal gas pressure from sublimating ice exceeded the weak tensile strength of the comet material at temperatures around minus 60 degrees Celsius. This temperature threshold explains why some comets survive close solar encounters while others disintegrate. Comet Lovejoy in 2011 passed just 140,000 kilometers from the Sun's surface, closer than Atlas ever got, but survived because it reached peak heating gradually. Its internal temperature rose slowly, allowing gas to escape without building catastrophic pressure. Atlas heated too quickly for this gentle outgassing. The fragmentation also exposed Atlas's formation history. Chemical analysis of different fragments showed varying concentrations of carbon monoxide, methane, and ammonia. This heterogeneous composition suggests Atlas assembled from materials that formed at different distances from the young sun. Some components crystallized in the cold outer reaches where nitrogen compounds dominate. Others formed closer in no, where water ice and carbon dioxide were the primary building blocks. Radio telescope observations detected unusual isotope ratios in Atlas fragments. The carbon-12 to carbon-13 ratio differed significantly from solar values. indicating the comet incorporated materials from interstellar space. These isotopic signatures act like fingerprints, revealing where and when different components formed in the early solar system. Infrared spectroscopy identified silicate dust grains within Atlas fragments. These particles showed crystalline structures that require high temperature formation, over 800 degrees Celsius, yet they existed in a comet that spent most of its life at temperatures near absolute zero. The contradiction suggests Atlas incorporated materials that traveled vast distances within the protoplanetary disk, from hot inner regions to cold outer zones. The debris field from Atlas continues expanding at roughly 1 kilometer per second. Computer models predict the fragments will spread across 10 million kilometers by 2030. Some pieces may eventually collide with asteroids or be perturbed into different orbits by planetary gravitational influences. Others will complete their 26 million year journey back to the Oort cloud carrying scars from their violent breakup. Meteoroid streams from Atlas may produce observable meteor showers on Earth within the next century. When debris particles intersect Earth's orbital path, they create brief streaks of light as atmospheric friction vaporizes them. The timing and intensity of these displays will provide additional clues about the original comet's internal structure and breakup dynamics. Professional comet hunters like Christian Sarnecki in Hungary documented Atlas throughout its death spiral. Sarnecki's observations from Piszkesteto Observatory revealed that individual fragments followed different brightness curves. Some peaked and faded within days. Others maintained steady output for weeks, before suddenly dimming to invisibility. These variations reflected differences in fragment composition and structure. Pieces rich in carbon monoxide brightened dramatically, but exhausted their volatile materials quickly. Fragments dominated by water ice showed more gradual brightness changes as they slowly sublimated in sunlight. The largest piece, designated Fragment A, contained enough material to remain active for over 2 months. Amateur astronomy networks coordinated global observation campaigns during Atlas's final weeks. The American Association of Variable Star Observers collected brightness measurements from over 300 volunteers worldwide. This citizen science effort provided time resolution impossible with professional telescopes, which must divide their attention among many targets. The data revealed rapid brightness fluctuations on timescales of hours. These variations correlated with fragment rotation periods, suggesting that different sides of each piece had different compositions or surface properties. Some faces were dark and relatively inactive. Others glowed brilliantly as fresh ice deposits sublimated in sunlight. Polarization measurements provided additional insights into Atlas fragment properties. Light scattered by dust particles becomes polarized depending on the size and composition of the scattering material. Atlas showed unusually high polarization, indicating dust grains smaller than typical comet particles. This fine dust likely resulted from the violent breakup process, which pulverized larger chunks into microscopic fragments. The European Space Agency's Gaia spacecraft, designed primarily to measure stellar positions and motions, also tracked Atlas fragments with unprecedented precision. Gaia's astrometric data revealed that different pieces experienced different non-gravitational forces as gas jets pushed them in various directions. These measurements helped astronomers understand how outgassing affects comet orbits and fragment dispersal. Japan's Hayabusa 2 spacecraft, returning from asteroid Ryugu during Atlas's active period, captured distant images of the fragmenting comet. These photographs, taken from over 100 million kilometers away, showed the expanding debris cloud as a faint smudge against the star field. The images provided important calibration data for ground-based observations. China's Chang'e lunar missions included instruments capable of detecting particles from Atlas during the comet's active phase. Dust detectors on the lunar surface recorded increased impact rates during April and May 2020, consistent with debris from the fragmenting comet reaching the Earth-Moon system. The Atlas event influenced comet mission planning at space agencies worldwide. The European Space Agency's Comet Interceptor mission, scheduled for launch in 2028, will target a dynamically new comet on its first visit to the inner solar system. Mission planners now include contingencies for rapid target fragmentation based on lessons learned from Atlas. NASA's Deep Impact mission in 2005 deliberately created an artificial comet fragmentation by slamming a copper projectile into Comet Tempel 1. The Atlas breakup provided natural comparison data, revealing that artificial impacts produce different fragment size distributions than spontaneous structural failure. The economic impact of Atlas's failure rippled through the amateur astronomy community. Telescope manufacturers had anticipated increased sales as casual observers prepared for the promised spectacular show. Educational planetariums planned special programs around the bright comet. When Atlas disintegrated, these commercial expectations evaporated along with the comet itself. Scientific impact proved more positive. Over 200 research papers have cited ATLAS observations, advancing understanding of comet structure, composition, and evolution. The breakup provided a rare natural experiment that would be impossible to reproduce artificially. No space mission could deliberately fragment a comet so completely while maintaining such detailed observational coverage. Ground-based telescopes continue monitoring the debris field where ATLAS once existed. Occasionally, dust particles from the breakup create brief meteor streaks when they encounter Earth's atmosphere. These tiny flashes represent the final chapter of a story that began before dinosaurs walked the Earth. The largest remaining fragment, now designated ATLAS A, measures roughly 200 meters across and continues following the original orbital path. It produces no detectable gas or dust, appearing as a dark speck against the star field. This inert remnant will serve as a gravitational anchor for computer models tracking the debris cloud's evolution over coming decades. The spectroscopic surveys of the ATLAS debris field revealed organic compounds previously undetected in comets. These complex carbon-based molecules, including formaldehyde and methanol, suggest that comet impacts may have delivered more diverse chemistry to early Earth than previously thought. The molecules survived the violent breakup process, indicating they were deeply embedded within the original nucleus. In September 2024, 4 years after ATLAS disintegrated, the Hubble Space Telescope revisited the debris field. Most fragments had faded beyond detection, but thermal infrared observations revealed dark objects still following the original orbit. These inactive remnants represent the rocky skeleton of what was once a brilliant comet, now stripped of their volatile icy mantles. Future deep space missions may encounter ATLAS debris during routine operations. Spacecraft traveling through the inner solar system must account for increased meteoroid hazards along the comet's former orbit. Mission planners now include ATLAS fragments in their hazard models for the next several decades. The comet that died in days took millions of years to tell its story.